I've created 2 example videos involving VSEPR problems. In this video, I don't draw the projection sketches, but in the other video I do. So if you're interested particularly in the projection sketches, I would encourage you to check out that second video. So in this video, we're going to look at a couple examples where I give you a molecule, and then I ask for the electron geometry, the molecular geometry, and the bond angle. So in all of these problems, the first thing we have to do is draw the Lewis structure. So actually what I would encourage you to do is pause the video, see if you can draw the Lewis structure, and then compare that to the Lewis structure that I come up with. So I'll take a second, let you pause the video. Okay, so the Lewis structure that I come up with is as follows. You want to be sure that you came up with the same one. So now to determine the electron geometry and the molecular geometry, I need to know the total number of electron groups and how many lone pairs I have. So I have 1, 2, 3 bonded atoms, 1 lone pair. So I've got a total of 4 electron groups and 1 lone pair. So I'm going to go to a table that's similar to one that you have in your textbooks. Right? And so I would look up here, okay, 4 electron groups. That tells me that the electron geometry is always going to be tetrahedral. And when I have 1 lone pair, that tells me that the molecular geometry is trigonal pyramidal. And the ideal bond angle in a tetrahedral electron geometry is 109.5 degrees. But of course, because the lone pairs are more repulsive than the bonded atoms, the bond angles in the trigonal pyramidal molecules will be less than 109.5. Now, in this video, I'm going to use this table, but of course, I need you to learn this table, and not because it will not be provided on quizzes and exams. All right, so if we fill in the information on the previous slide, so we have a tetrahedral electron geometry, a trigonal pyramidal molecular geometry, and a bond angle of 109.5. Right? Now, not only do you need to know the names of these geometries, but you also need to be able to picture these molecules in 3 dimensions in your head. So I'm going to go to this website that you've seen in another one of my videos, a great video here from Ohio State University, where we can look at models of these molecules from VSEPR theory. So here I have a tetrahedral molecule, but of course our molecular geometry was not tetrahedral, it was trigonal pyramidal. So we lose one of the bonded atoms to become a lone pair. And so this is what our trigonal pyramidal molecule is going to look like. And so I encourage you highly to investigate this page and play around with these molecules, spin them around, and see what these molecules actually look like. All right, let's go back to the PowerPoint and look at another example. All right, now we want to do ozone, O3. So again, I'd pause the video, see if you can come up with the Lewis structure. All right, here's the Lewis structure I come up with. So now I've got 2 bonded atoms, 1 lone pair. So I've got 3 total electron groups with 1 lone pair. If I go to the table, 3 electron groups tells me the electron geometry is trigonal planar. If I have 1 lone pair, the molecular geometry is bent, and the bond angles are less than 120 degrees. And we've got our answers filled in here. And again, I'm going to go back to that website and take a look at what this bent molecule looks like. Okay, so trigonal planar would look like this. All 3 terminal atoms are in the same plane, but when I have 1 lone pair, these bent molecules look like this. All right, I'm going to go back to PowerPoint. And look at another example. All right, sulfur hexafluoride. So again, pause the video, take a second and draw the Lewis structure. All right, here's my Lewis structure. So around the central sulfur atom, I have 1, 2, 3, 4, 5, 6 bonded atoms. No lone pairs. And so when I go to that table, 6 electron groups tells me the electron geometry is octahedral. If I have no lone pairs, then the molecular geometry is also octahedral, and the bond angle is the ideal bond angle of 90 degrees. All right, let's see what an octahedral molecule looks like. And again, there's a typo on this page. It's the only big problem with it. You see trigonal pyramidal here twice. This second one is actually octahedral. And so this is what an octahedral molecule looks like. And so all the atoms in an octahedral are identical. Right? It may look like these 4 in the plane and the 2 on the outside are different, but if I just rotate this 90 degrees, more or less, right, we can see all the atoms are in fact identical in the octahedral electron or molecular geometry. All right, we've got one more example. And that is ICl3. So one last time, go ahead and pause the video, see if you can come up with the Lewis structure. All right, here's my Lewis structure. So now I have 1, 2, 3 bonded atoms, 2 lone pairs. So I've got a total of 5 electron groups with 2 lone pairs. So 5 electron groups tells me that the electron geometry is trigonal bipyramidal. 2 lone pairs tells me that the molecular geometry is T-shaped. And so remember, in these trigonal bipyramidal molecules, when I have lone pairs, it's the equatorial atoms that come off first, not these axial atoms. All right, and so here's our answers. And then again, one last time, let's go and see what this molecule looks like. So a trigonal pyramidal would look like this. And again, all the atoms in the trigonal bipyramidal are not identical, right? These 2 axial guys are not the same as these equatorial ones, right? If I try to rotate this guy 90 degrees, you can see, yeah, I'm not reproducing the molecule. And so when we have lone pairs, the lone pairs preferentially replace these equatorial atoms, not the axial ones. So if I had 1 lone pair, which was not the case in our molecule, I flipped it around a little bit on us, but here's our seesaw molecule, and you can see these atoms are bending in slightly, and that's because the lone pair is more repulsive than a bonded atom, right? And so our bond angles are going to be less than 90 degrees because they get squished together. And then the T-shaped molecule is going to look like this. And again, the 2 atoms that would have been here would have been in the equatorial planes. And again, you can see this guy is bent a little bit because the lone pairs are more repulsive than a bonded atom would be, and it causes the rest of the atoms to squish together a little bit. All right, and that's it for this video of VSEPR examples.